Hello and welcome back. In the previous lecture, we looked at the FEM solution of Poisson's equation by using an Excel sheet. So now let's extend this Excel sheet to the convection diffusion equation as well. So please open the Excel sheet before you start this lecture. And so now let's begin. So the convection diffusion equation can be thought of as being derived from the scalar transport equation. You could think of it as a special case of the scalar transport equation. So let's derive the scalar transport equation first. Most of the heavy lifting for this we have already done when we studied finite volumes. So we looked at the conservation statement, we looked at diffusive flux, convective flux, source terms, we looked at the divergence of flux concept. So we have done most of the heavy lifting already. But in finite volumes, we just ignored these terms because we were looking at a purely diffusive case, which you could think of as a heat flux problem, as a heat diffusion problem, or as a mass diffusion problem, right? So now let's turn our attention to more complicated problems. So while we'll be dealing with 1D solutions only, so let's extend our thinking. So now let's think of a fluid flow through a pipe, okay? Because now we are thinking about convection as well. So we could think about that. So now if there is some species which is mixed inside this fluid, so and we want to write a mass balance for that species, the procedure would stay the same. So we would still be writing this kind of a balance equation, and then we would just be expanding those terms. Divergence of the convective flux, divergence of the diffusive flux, the source term, the rate of change. It's just the same idea once again. So instead of writing, so here I have written the scalar as x, which is the mass fraction, because we are writing a mass balance, right? So each of these terms should have a unit of kg per second. Okay, so you could think of a scalar as x here because the density might be changing, right? Because as the mass fraction of that species changes, so the density of the fluid might change. Okay, so the density is not constant, but you could think of though it is a scalar, of course, but it is not constant. The main scalar that is varying is basically x, okay, which is your mass fraction. So let's try to extend this idea to a generalized scalar phi, okay. And then by doing a very similar conservation statement, you can come to this kind of an equation, which you could think of as a scalar transport equation. Okay, but we just have to be careful, like when we apply this to specific physics, we just have to make sure that it represents those physics. So for example, if I consider phi is equal to x, so it might fit here, but it won't fit this term, okay, because the Fick's law of diffusion says the flux is minus k del into concentration. Okay, so here I will need to write rho x, right? So similarly, if I am writing a heat balance, so this might be minus k del T. So here phi is equal to T, but here I will have to write CPT, right? The specific heat into temperature. So you just have to make sure that the physics is representative. But in general, this is the way you write a scalar transport equation. And then we'll just rearrange and write it in this form. Since the volume integral is applied over each term, we can also say that inside the control volume at every node, this equation holds. Okay, so this is the form of the scalar transport equation. So now let's look at the special case, which is the convection diffusion equation, and for that we'll have to look at the incompressibility assumption. So before we can reach there, we'll have to write a mass balance, right? Because to actually make a statement about incompressibility, I will have to write a mass balance. So here, instead of the species mass balance, let's think about the fluid itself. Okay, let's think that there are no species which are mixed in the fluid. Okay, so there is only the pure fluid. Okay, so in that case, this kind of a mass balance can be thought of to simply reduce to this kind of an equation. Okay, so here your x can be thought of as 1 because it is purely one fluid. So the mixture mass fraction, which is your x, could be thought of as 1, and there is no diffusion when you consider pure fluid, right? Fluid doesn't diffuse into itself. And also there is no source term, so you would get this kind of an equation. Now let's make the incompressibility assumption, and say that density is constant. That is basically the incompressibility assumption. So when you put density equal to constant, your equation would simply reduce to this, and then you can say at every node del dot u is equal to 0 is holding, right? So now this allows us to make our convection diffusion equation more compact. So if I just expand this by this blue term by the product rule and delete the term scaled with del dot u, because now it's incompressible, so I can do this, I would get this equation, and with further simplifications I can like constant k and steady state no source, so I can just get the simplified form, that is the convection diffusion equation. Okay, so now we are interested in solving this differential equation in 1D in a very simple and similar case. So at x equal to 0, phi is equal to 1, and x equal to 1, phi is equal to 0. These are the same boundary conditions as before. My length now I have taken as 10, but I want this domain to still run from 0 to 1. So I'll just normalize it. I'll take L outside for each of these x terms, dx terms. And then by doing this normalization, I can just rearrange. So this blue part is what depicts the convection. So note that the convection is in the, that is the velocity is directed in the positive direction. Okay. So here we must talk about what is upstream and downstream. So x1 is upstream and x4 is downstream. Okay. So this distinction is really important because now we are using convection. So the numerator of this term, this scaling term, is basically the convection effect. The denominator is the diffusive effect, and the ratio of both of these is basically UL by D, which is also called as the Peclet number. So the idea is that as Peclet number increases, the system becomes more convective, and as it decreases, it becomes diffusive. Okay, so if your Peclet number is low, and let's consider there is perfect plug flow in this channel, which means that the velocity is just constant everywhere. This is an ideal case, not a real case. So if I just take a concentration pulse and I allow it to advect with this velocity, so due to the diffusion at low Peclet number, I will just get this smearing of this pulse in like a Gaussian. Okay, so this will be a Gaussian curve, and as I go on increasing my Peclet number, this smearing will be less and less, and it will be very sharp at high Peclet number. So there is a very strong gradient at high Peclet number, and because of this it is more difficult to model, and you will need a lot of points here. Okay, so now let's look at a real CFD simulation in finite elements where we are facing this problem. So let's take this case, which is a case, let me explain the case first. So here you have a CFD simulation of Navier-Stokes equation, fluid flow in 2D, and there is a reaction taking place. A plus B gives C. All of these A, B and C are perfectly miscible in water, and the change in density due to the reaction is minimal. So you are solving this coupled problem, and A comes, so A reactant is coming from the downside of this T, and B is coming from the upside, and they mix in this T, and C is formed. Okay, so there are sharp gradients of C formed suddenly when the mixing takes place, and this is a transient simulation, and we are trying to capture the dynamics, and the real mixing takes place after this obstacle. Okay, because this obstacle causes the flow to break and mix together. Okay, so now this is the flow, and let's observe. So just observe these values here, the scale bar. So you can see that the scale bar is actually going from negative to positive. Now negative concentration makes no sense, right? And this negative value is pretty strong. So if I am looking at, for example, the negative value, it is minus 0.33 and the positive value is 97. Okay, so there's a really strong negative value here, and which is aphysical because the concentration cannot go negative. So let's look at where this negative value exists. So if you look at just after the mixing starts occurring, there are strong concentration gradients of this product C, and the system is not able to model it. Okay, and that is entirely because of the similar convection diffusion case, because here we are using the fluid flow velocity as the velocity in your convection diffusion equation. Okay, convection diffusion equation for the species balance for this C. Okay, So now let's try to understand why these oscillations occur. Okay, so you can see these oscillations here. So there are positive, negative oscillations, right? And they are failing to model that sudden jump. Okay, so we'll understand this on an Excel sheet. So please open this Excel sheet and look at this convection diffusion part. Okay, so there are many tabs and we'll study all of them. So look at the third tab, that is the convection diffusion. And this is exactly the same equation. So now we'll have to understand the FEM formulation first. So let's quickly just show what is the FEM formulation. So this is your strong form. You multiply by a test function and you integrate it. So now you just have one more term here. Okay, and you don't apply integration by parts here. So this term will just be integrated as is. So this is the term which I have included in these stiffness matrix terms. So these first two terms are the diffusion terms which you have already seen in your Poisson solver, and these two terms are your convective terms. So they are scaled with this G16, this guy, which is your Peclet number. Okay, so now let's see how this solution changes. Peclet number is set to 0.1, which is a very low value. So this is almost like your diffusion case, almost a straight line like we solved in FEM and FDM. So now let's increase this and we'll start seeing the dynamics. So now you can see the oscillations are starting. Okay, and these are the same oscillations which are occurring when the system is trying to model any steep gradient. Okay, this is also because this Galerkin works more like a central difference scheme. Okay, so let's try to understand this a bit more. Okay, and for this we have the other tabs as well. Okay, so let's look at these tabs. So in the diffusion only tab, I have only kept the diffusion terms in the stiffness matrix terms, and in the convection only tab there are only the convection terms. So now let's understand their effects separately. So in the diffusion only tab, if you look at the local stiffness matrix and the global stiffness matrix, so I have highlighted them. Okay, so you can see the formation of the local stiffness matrix. So you can see diagonally dominant terms here. Okay, so the negative terms are off diagonals, and on the diagonals these are the dominant terms. Okay, so if you just add them, you will get a diagonally dominant global matrix. Okay, the diagonals are dominating. So what does this mean? So if I am looking at node 2, I am highlighting this equation here. Okay, which is the equation for node 2. Okay, so here u2 is getting multiplied with your diagonal term. Okay, and this is the equation which is basically telling you about the dynamics at node 2, and you are seeing that u2 is being scaled by a higher value, and so this is easy to solve because these equations are representative. So the equation for u2 is giving a good representation for u2. Okay, the scaling is good. But what would happen in a convection case? So this is the stiffness matrix. So here you are having minus on one of the diagonal terms as well. Okay, so you have minus in the upstream direction and you have plus in the downstream direction. Okay, so this is a bit different, and when you try to take the global stiffness matrix for that, you are getting this kind of a case. Okay, so what you're getting is basically almost zero terms at the diagonals. Okay, and so if I try to highlight this equation for node 2, so u2 is getting multiplied by almost 0, which means that this equation is not really representative of u2's identity. Okay, it is actually representative of u1 and u3's identity, and somehow the solution is trying to derive u2's value from the other two nodes. Okay, so that is causing node to node oscillations. So this is the problem, one way of looking at the problem. So the way to solve this is what is called as upwinding. So let's look at what happens here. So this is the convection diffusion case. Again, I am highlighting this. Okay, these three terms. So you can see that the diagonal is not dominant in the convection diffusion tab. You can see the diagonal is not dominant. This is 15 and this is 10, right? So the diagonal has lost its dominance. And if I take a higher Peclet number, this increases even more. Okay, right? So now the diagonal has become really small. So one of the ideas to solve this is called as upwinding. So let's understand the intuition. So let's say if you are drinking water in a river and somebody pollutes the water 10 meters upstream, then that pollution will get carried to you. It will be a problem. But if it is 10 meters downstream where the pollution is occurring, then it doesn't matter. This is really showing you that the information propagation is from the upstream to downstream. Okay, so you should have more. You should have a skew in the information capture in the upstream direction. That's the idea. In case of, for example, a lake in which is still. So if the pollution is occurring close to you, it will spread to you by diffusion. It doesn't matter in which direction it is occurring. But in case of convection, the direction matters. And so here what you are seeing, if you look at especially these two terms, you can see that as we go from 1 to 6, there is the basically you are going from upstream to downstream, right? So if we just look at these two terms, this is the upstream term, this is the downstream term. Downstream term is having a higher scaling and upstream term is having a lower scaling. So if you do upwinding, this will just transfer here. The downstream guy will get pushed down and the upstream guy will get pushed up. So the diagonal term will again get dominance. Okay. So the way to do this in finite elements was shown by Brooks and Hughes in a very landmark paper. And before this, really, it was difficult to use finite elements for convection diffusion kind of cases. But after this SUPG was invented, this was really landmark, and this really changed everything. So let's try to understand SUPG. So this is streamline upwind Petrov-Galerkin. So this is a Petrov-Galerkin formulation. So here we are modifying the test function. So here in continuous Galerkin, your test function was psi. So here we are using psi plus u dot del psi. So you are taking a derivative of this psi, you are projecting it along the velocity. Okay. So in 1D case, this is very simple because the d psi by dx are simply piecewise constants. One is positive, one is negative. So scaling it with u and adding it would simply work like this. So the positive slope polynomial will just shift up. The yellow polynomial will shift up and the white polynomial will shift down. So let's just look at two elements now. So what would happen at this node? The upstream node is getting more, the upstream direction is getting more weighting and the downstream direction is getting less weighting. Okay. If you write the equation for this node, you will just see that. Okay. But you are also seeing this discontinuity now. So this assumption, which was the continuous assumption, we could use integration, but here it is very difficult to integrate at this part. Okay. So we have to develop a specific FEM formulation for this. So let's write this as let's write the strong form as f, and then let's write these test functions, multiply this by f. So we'll multiply each of these test functions by f, divide it into two terms. The first term is continuous, right? Psi is continuous, so we can just use our standard Galerkin's representation here. And this term is discontinuous. So what we say is that this term is thought of as an approximation which is integrated only inside the elements. Okay, it is not integrated over the entire boundary. It's just element to element integration. It's like an approximation, you could say. It is scaled by tau. Okay, so this tau is really scaling your approximation here, and you are not applying integration by parts. Okay, because there is no boundary involved. This is just inside the element, and so you are just using the strong form. So now let's understand this a bit. So this is your blue term, right? So your SUPG term. So if you are applying linear elements and you use a strong form, you have a second order derivative. So this goes to 0. Okay. And even if you are using quadratics, then this would not go to 0. But we are anyways integrating inside the element, so the direct deltas issues won't come about. Okay. So now and we are also scaling with tau. Okay, so remember that. So now let's look at only the linear case and let's expand this term. Okay, so you would get a term like this. Let's write down this in matrix format, and now you are seeing a matrix structure which is very similar to the diffusion stiffness matrix, because you had a k11 term in that which was d psi 1 by dx into d psi 1 by dx, then k12 which was d psi 1 by dx into d psi 2 by dx. So it's exactly similar, just being scaled by u, both of these terms. Right, and more specifically, this is u dot. Okay, which means this is acting in the direction of velocity. So that is why this is called a streamline diffusion. So this is like diffusion acting along the velocity direction. So now let's apply this. Let's go to our Excel sheet. Let's apply exactly that same formula which I showed. And if we write this in the local stiffness matrix, so I have an SUPG tab here which shows that. And if you write the global stiffness matrix, you can see that you have recovered global dominance, the diagonal dominance. And add this to your convection diffusion, and now you can see something interesting, that look at these two terms. So here you can see that the upstream term, so previously we looked at these same terms, and we saw that this term was 10, this term was 495, right? So now this term is 499, this term is almost 0. So the downstream guy has been pushed down and the upstream guy has been pushed up, and so the diagonal dominance is recovered. And now we can actually look at the solution. Let's try to model this. So now if I just put Peclet number equal to 1, I'm getting a good fit to the analytical solution. Peclet number equal to 10, 15, 100, 500. So it gives nodally accurate values for any kind of Peclet number. So we have to understand what is this tau here. So this tau is obtained from abstract finite element analysis, and these you will find in research papers or in books, and you should use the tau from those books. But in CFD softwares, you can arbitrarily tune this, but it's better to instead of arbitrarily tuning it, you just find the value from the literature and use this. Then you would get really nodally accurate values. Okay, and now let's look at the same problem solved with SUPG. I'm sorry. So this is the problem, and now you can see in this CFD simulation, though there are strong gradients, there is no minus sign, there are no oscillations. So this is how this is why SUPG is really so crucial for CFD simulations, and this is what I wanted to show here. So only some few things like error analysis are now remaining, and we'll see that in the next lecture, and we'll end with some closing statements. So let's meet again in the next lecture, and I thank you for your attention.